Welcome to springlib.
In this problem, we are given descriptions of 4 different reactions, and we want to determine first whether or not the reaction will occur, and we secondly want to determine for the reactions that will indeed occur what the values are for the cell potential and change in Gibbs free energy at standard conditions, as well as the value for the equilibrium constant K at 25 degrees Celsius. So the way that we need to determine whether these reactions will occur is whether or not they are spontaneous. So we need to first calculate the cell potential, and we know that for positive values of the cell potential, that corresponds to a spontaneous reaction that will indeed occur. So in part A, we have I2 crystals being added to a solution of NaCl. So I2 in the form of crystals must mean that it is a solid, and NaCl means that we have Cl minus ions in aqueous solution. So we can look up the 2 half reactions that corresponds to from our standard reduction potentials table, and we know that we have to have I2 being reduced, and we also have to have Cl minus being oxidized to Cl2. So we have to flip the sign of the reduction potential for that half reaction, and when we do that, we can now combine these 2 equations to find the overall cell potential. And when we add those 2 standard reduction potentials together, we see that the cell potential comes out to negative 0.82 volts. And since that cell potential at standard conditions is less than 0, this is non-spontaneous. And that means that this reaction will not proceed unless we supply some kind of energy. So that reaction will not occur for that reason, that it is not non-spontaneous. Now, part B, we are told that we are putting Cl2 gas into a solution of NaI. So this time we start with Cl2 gas, and we have I minus in solution. So from the half reactions in the standard reduction potentials table, we have to have Cl2 being reduced this time, and we also have to have I minus being oxidized to I2. So that is why we have to flip the first half reaction, and when we do that, we can add together the standard reduction potentials, and this time we see that the overall cell potential at standard conditions comes out to a positive value of 0.82 volts. And so now, since the value of the cell potential is positive, greater than 0, we know that this reaction will proceed spontaneously, and so this reaction will occur. And now we need to calculate the value for the change in Gibbs free energy. Again, this is the overall reaction, so we can eliminate those 2 electrons. So when we combine that together, we have Cl2 gas plus 2I minus aqueous going to I2 solid plus 2Cl minus aqueous. That is the overall reaction. And now to find the change in Gibbs free energy, delta G, at standard conditions, that's just negative NFE. N is the number of moles of electrons, and from that equation we canceled out 2 electrons. And Faraday's constant is 96,485 coulombs per moles of electrons. And the cell potential we found was 0.82 joules per coulomb, which corresponds to units of volts. And so now when we calculate that all out, we should get delta G in units of joules, and if we divide by 1,000, we can get it in units of kilojoules, and that comes out to about negative 160 kilojoules. And finally, we want to determine for this reaction what the value is of the equilibrium constant K. We know that the non-standard cell potential will be 0 at equilibrium, and the cell potential at standard conditions is 0.82 volts. We plug this into the Nernst equation, so we have 0.0591 over n, which again is 2 moles of electrons, times the log of K, since we are at equilibrium. Now, if we rearrange this equation to solve for the equilibrium constant K, then we should get a final answer of about 5.6 times 10 to the power of 27. In part C, the reaction that is occurring is a silver wire, so that means solid silver, is placed into a solution of CuCl2. So we have solid silver, and we have Cu2 plus ions in aqueous solution. So from the standard reduction potentials table, we know that these are the two half reactions that are taking place. Silver is being oxidized since it starts out as a solid into Ag+, and Cu2+, therefore, must be being reduced. So now if we calculate the cell potential after rearranging the two half reactions appropriately, we see that the cell potential comes out to negative 0.46 volts. And just like part A, since the cell potential at standard conditions is less than 0, that means this reaction is non-spontaneous and will not proceed without an input of energy. So no reaction occurs for parts A and C. And the reaction in part D is FeSO4 being exposed to air. So that means we have Fe2 plus in aqueous solution ions plus gaseous oxygen from air. And so these are the half reactions from the standard reduction potential table. We know that oxygen is being reduced to water, and iron is being oxidized from Fe2 plus to Fe3 plus. And so this time when we calculate out the cell potential, we see that it comes out to a positive value, meaning this reaction will occur since it is spontaneous, of 0.46 volts. And so we can write out the overall reaction, since we know that this reaction will occur. We multiply the second equation by 4 to cancel out 4 electrons on either side. And the overall reaction taking place is 4 Fe2 plus aqueous plus 4H plus aqueous plus O2 gas going to 4 Fe3 plus aqueous plus 2 H2O liquid. So that is the overall cell reaction. And now, since this reaction occurs, we need to calculate delta G as well as K. So again, delta G at standard conditions is equal to negative NFE. This time, we have 4 moles of electrons that we canceled out, so N is 4. Faraday's constant is 96,485 coulombs per mole of electrons, and the cell potential is 0.46 joules per coulomb. Now we can calculate out the change in Gibbs free energy at standard conditions. If we divide the result by 1,000, we get it in units of kilojoules. That comes out to negative 180 kilojoules. And we can verify from the negative value of delta G that this reaction is spontaneous. And for K, we use a Nernst equation again, knowing that the cell potential will be 0 at equilibrium. And at standard conditions, the cell potential is 0.46 volts. And then that's minus 0.0591 over n, which is 4 now. And then times a log of K. So now we can rearrange that equation to solve for the equilibrium constant K. And we should get a value of about 1.3 times 10 to the power of 31.